And thanks so much for the previous two speakers. And I really listened about this kind of process. The process. What was that word? Supervision of RL training. Thanks so much for their speaking. And so since they have given you guys lots of ideas and introduction to what kind of thing is RL and what kind of thing is modularity, we also learned from the community and we grew together. Yeah, and what I want to introduce is some recent updates on a topic, what we are moving forward on large scale MOE model training. So take the thing back, let's think about why we need modularity from the MOE side. As we all know, MOE models, the parallelism per strategy for MOE is quite different, like for dense model. Like for MOE model, you heard the words like EP, right? You heard the words like the MLA, or you heard the word like the data parallelism attention. Um, at the long beginning, this kind of thing has been utilized into MOE inference for a long time. And compared with vanilla parallelism, these kinds of parallelism for MOE model actually accelerated MOE model's inference a lot. But a sad news is that for long period of times, RL frameworks do a bunch of things. We right now call it invasive modification to inference engines. That makes this kind of latest optimization of MOE models parallelism cannot be directly utilized. So today, the first principle I like to share about everyone is like making things modular, or in other words, do not do invasive optimization or modification to Megatron, to FSDP, to SGLang, or to whatever kinds of inference engine, training engine. The idea behind this, like, RL should be the clue behind training and inference. The ideal thing is like you just need to connect them together. There's not so many things that you need to do. You need to optimize. Yeah. So I think to be humble and to get the first principle, try to make your things clean and elegant. Yeah, do not do invasive modification to any backend. Okay. That's the first principle. So take this. Uh, wait, what's up? Okay, thanks. So, uh, yeah, take this in mind that I would like to introduce our RL frameworks. We call it Miles, and is brother or like the father of it is named of slime. Have you guys heard about what is slime? Slime is like a little monster that is you can scratch it and it's actually fluid. Yeah, so we limit slime is just like we want our IO frameworks just connect the training and inference, and there's no much things that you need to do. If you just elegantly connect them together, it should work efficient as it does. Okay, so for our systems, we just define our system as 5 parts. The first thing is like starting from the RL process is like a rolling out. We get we sample data from your data set and send it to SGLang router. SGLang, it is like SGLang router is a black box inference connector to send all the requests to underside SGLang server. But I want to stress that, as I just said, do not do invasive modification, by which taking practice. For a long time, there are some RL frameworks utilizing underneath SGLang's components, like model runner, like SGLang engine, like even a synchronized SGLang engine or whatever thing you name it. But these kinds of components, indeed, there's lots of I call it invasive changes to the main repo. And we want users using SGLang router. It is just because you take SGLang as a black box. You do not do anything more invasive to SGLang. Then when a new model released, for example, if DeepSeek V4 released, yeah, then you just update SGLang's version, and that model should be running in your RL pipeline immediately, right? Since you did not modify synchronize of SGLang, so you just use the latest SGLang as long as SGLang CI is stable. Okay, so that's we use SGLang router and SGLang server rather than SGLang asynchronized engine or SGLang model worker. These kinds of strange classes. Yeah. And another thing about SGLang router I want to share is that SGLang router is a way to align your training with your serving. This is different from the topic I will say of training inference mismatch, is the training serving alignment. So the idea is simple. How do you train your model? is expected to be how you are serving your model. If you expect your users using your agents like round A, round B, round 3, then you need to train it with it. Yeah. So using SGLang router is a good way that when your agent is being trained, you just deploy it with the SGLang router. So everything, the the components you use for training and it is exactly the same components you use for serving. That makes sure that there's no gap between your training and your serving. Then what you train is what you gain. And if you train a good agent, it should be deployed immediately as a good agent online. Yeah, that's I think that's also an idea like uh try to do a training and serving alignment with SGLang router. Yeah, and also it's connected with modularity. Do not do invasive changes to the rollout side. Yeah. Come this back, like take the principle. Just after rollout, store the data in the data buffer, and then train it in Megatron and Megatron or train it with FSTP or Torch Titan and then put the weights back. Yeah, that's all you need for the RL. Yeah, so we just build these kinds of black lines and all these green lines and these red lines should not be what we do, right? Just let these kinds of elegant guys evolve themselves and we just take advantage of them. I think it's a good and smart way to do with RL. And I actually yeah, we see that this year a bunch of these kinds of RL frameworks have more we yeah, it's common sense that we are moving to this kind of modularity design. um so uh come this back. This is our RL framework, and these blue lines. Oh wait, these blue lines is what I want to share today. Since sorry, I think this one is line one. Since the first, the second, and these two has been described in other places a lot of times by myself. So I like to introduce this kind of training for mismatch, speculative decoding RL, and multi-agent training and FPA training, whatever. So the principle is that there's no invasive modification, so everything moves much faster than we expected. And another thing is that uh, mm, given modularity design, if you follow the first principle, if you think something should be working like that, you just implement it into rollout and don't need to do in the training side. Okay, so let's do the first thing, like the training first mismatch. Uh, So, what kinds of things training first mismatch? This is a commonly hated words in academia and in somehow frontier labs a lot. So it means that um, ideally speaking, that Megatron do forwarding and SGLang do forwarding. So why couldn't you using Megatron's forwarding to do this to do rollouts? Like every time you're using Megatron forwards, get the logic, sample it, and append it, and then do the forwards. The idea is naive because Megatron cannot support these kinds of like KV cache management or like this kinds of continuous batching, these things. So we have to separate training engine and the inference engine. Training engine we have to separate training engine and the rollout engine. Training engine is this kind of powerful engines like Deep Speed, Torch Titan, Megatron. They are good at forwarding in large batch size, but they are not good at KV cache management. And the inference engine is like we care about continuous batching and we care about KV cache management and other kinds of things. So that means even though training and inference somehow doing the same thing forward, yeah, but we shall using them differently. And due to this kind of difference underline, like I said, whether you need to manage the KV cache, whether you take different paradigm side, gradually speaking, for a same sequence, your forwarding results shall be different. Yeah. And yeah. Am I describing it right? Since you have to use for the same sequence, you should using training engine and inference engine to do the forward, but they behave a slight different, like kernels, like parallelism strategies. So layer by layer, your training inference engines probability for the same sequence could be different, and that's actually a bad thing for RL um since we are caring about the online unpolicy RL. So the ideal way is that online unpolicy means that we want to use the same model to be trained than to sample. But since the sample model's log probability is slightly different than the trained model, so this introduced a kind of off policyless. And that's what train-infer mismatch is trying to solve. Yeah. And people may have been spending over 8 months to discuss how to solve these problems. And here we want to share about our two solutions that train-infer mismatch is being controlled under our Miles framework. So the first thing that, as I said, train-inference mismatch is due to different kernel setting or paradigm strategy setting of training engine and inference engine, right? So the good thing, the first thing that you can try to align them. You use the same kernel for SGLang and for Megatron, and you use the same paradigm strategy for SGLang and for Megatron. Does that make sense? Yeah, of course it should make sense, but the engineering work underlying is quite burden, right? So the idea is like for SGLang it has SGLang's kernel, and for Megatron it has Megatron's kernel. And right now we change all these kernels into the same set of kernels and sets lots of things like batch size equal, and then with this carefully created changes, the log probability of SGLang's forwarding and Megatron forwarding and FSDP's forwarding can be exactly the same. And then we solve the problems partially. Yeah, as I said, because you can hear that we change a lot of things like the kernels, like the paradigm strategies, and so on. So this makes actually your training quite slow, because if you use the same thing for training inference, of course you guess either way training will be slow or inference will be slow. And another killing thing is like for MOE models, things can be much more complex, since you have something like the routing, have even EP, or you want to enable much more complex paradigm strategy. So this is a disclaimer, and I do not want to overclaim our projects. For this work, we call it truly on policy. Currently, we support FSDP model on dense LLM and FSDP with VisionX model on dense model, and also we support Megatron SGLang on dense LLM. Yeah, and for the other things, it's really complex, and it's like a yeah. So somehow each combination from your decar production is something that we want people to work on. So this is not a scalable solution to training inference mismatch, but we can solve it. Okay, we can still spend some time solve it. And another way to solve it is like we admit the existence of training inference mismatch, and we try to use the algorithm to solve it. So that's why I love RL. It is like a problem can be solved in an infra way or in an algorithm way. And this work we call it training. We call like the MIS or TIS you have heard. We utilize a traditional algorithm called importance sampling to solve these kinds of off policies. Yeah, sorry, this line here has some slight difference. It does not do truncation, but the idea is that we're using importance sampling to do a diverge that to correct back the difference between SGLang and between Megatron. So that makes the training inference mismatch somehow can be controlled. Yeah. So you can see this kind of solution should be much more easy to implement. It does not introduce more than 30 lines of code to solve it. Yeah. And so remember, we have two solutions right now, and we want to solve the problem training inference mismatch. Yeah. And the first solution is do a truly on policy. We align everything between SGLang and between Megatron. The problem is solved, but it's too much burden. And another way is that we're doing algorithm solution to the training inference mismatch. Yeah, and this is a traditional importance sampling ratio. Yeah, I do not want to dive so much into it, but you can remember the form is so elegant, right? Everyone can remember it. Just do a diverse, right? No more thing you need to do. Okay, so that's the first work I want to introduce, training inference mismatch. Yeah, and some funny news is that I want to share is that though I sharing the training versus mismatch, and the first thing in this talk, the idea is not sharing that we have so many problems introduced by training versus mismatch, but we are providing the tools for researchers and for RL workers that try to debug with their RL framework. So in my experience and our collaboration with the AI, and we found that using Miles in the post-training process, we never won in industrial level making Miles collapse due to train-infer mismatch. We spent over 3 months running over 40 sets of experiments, and we run over 3,000 runs of our experiments, and we finally found out one way to make miles like collapse due to train-infer mismatch. We make this out that we want to make sure that even this kind of 1 out of 300 failure can be solved with our tool. Yeah. Uh, so yeah, I jumped this not because they are not important, but because I've said it in a lot of places, and maybe you can search my name on YouTube, and I have a video on PyTorch conference that describing these ideas. Yeah. Uh, so let's go to some recent updates of what we do for the RL. Okay, so as I said, modularity means that you do not invasive optimization with inference engine or training engine. So uh, for inference, we spend a lot of time trying to implement speculative decoding because speculative decoding is efficient and accelerates your inference when with small batch size. Yeah, and another thing that for for RL, ideally speaking, we want to make sense in a large batch size. But the bad thing is that a bunch of times RL inference or sampling is being bounded by your environments. Because like you're sending an HTTPS to your agent Docker, then the response time of that Docker is not controlled by yourself. Yeah, so sometimes RL rolling outs can be in a small batch size. So like for each server, there's only no more than 10 requests running at this time. So that makes speculative decoding valuable for RL. Yeah, so I have proved why speculative decoding should be valuable, then how to make it actually happen. The idea is that use the latest version of SGLang and directly launch it. And that's since we do not do invasive modification to SGLang in miles, then ideally speaking, all the latest version of SGLang can be utilized into miles directly, and that's what happens. So we directly enabled SGLang speculative decoding in the RL process. And the good news is that our inference time just goes up. Oh, sorry, our inference efficiency just goes up, right? Our sampling time goes down. So is that the end? You may care about whether our reward gets hurt because we are enabling a new feature into RL sampling, but it has been proven by Google that speculative decoding is lossless. It's a 100% it's 100 accuracy solution compared with your naive sampling. So accuracy is right. So think about this. If we directly launch SGLang speculative decoding in the RL process, what we gain? We are faster, and what we shall lose? Seems like there's nothing we lose. Yeah, but take a step forward. Like I write I there I write 3 lines of experiments to compare the things with or without speculative decoding. The the green line is do not enable speculative decoding. And the blue line is enable speculative decoding, but frozen the draft model. Yeah. I, I want to spend just several lines to describe what is speculative decoding. Speculative decoding is like you have a small draft model that to draft a long context, really soon, and then you use the actual model you want to do sampling, the verify model to verify the context. If everything goes well, then it accepts as it's generated by the large model, but it sometimes gets rejected and then you need to regenerate it. Okay, so that's the idea of speculative decoding. It has a small draft model and it has a large verified model. And to make it quick, we should try to make sure that the distribution of the draft model should align closely with the distribution of verified model. If the distribution gets gradually shifted and shifted, then your speculative decoding does not make sense because if every draft your draft model make is being rejected, then it's actually did not accelerate it. So come this back, we have enabled SGLang's speculative decoding into RL, and this gets the blue line. But the blue line means that we frozen the draft model while the verified model is being trained. Since every time your verified model is the large model actually being trained, then the verified model gets shifted and shifted. Then your draft model stay the same. Then their distribution gets it gets shifted. Then speculative decoding would be slower and slower. Yeah, and then we design a new format of speculative decoding into RL. We call it online SFT. Yeah, online SFT means that we we define a conjunction loss for the draft model, and at the same time we train the verified model. You do not need to know what the actual loss it is, but the idea is that we want to make sure that these two models moves together, so their distribution shift would not expand. So that's the line of the red one. Yeah, red one means that we train the verified model and we train the draft model even though not the same rules, but they are being trained together. So the good thing is that they stay really close, and speculative decoding continue to give us speed up. Yeah, and this line is showing that with our conjunction training of speculative decoding, the draft model and verified model, our acceptance actually gradually goes up. So that means our speculative decoding gives more power when RL is continuing. So that's the second thing I want to introduce today. We enable an elegant way to enable speculative decoding in RL, since we do not do invasive modification for SGLang. So just clone the latest SGLang and turn it on. Yeah, it works. And then to make it even better, we define a loss to train the draft model and the verified model at the same time. It gives you a complete story, and this looks really nice. Yeah. Thanks. And this experiment is being performed with Mimo 7B model. It's the smallest model, maybe have MTP layers, open source. But we have also running experiments with like gigantic GLM 4.5 models, and it also works. But yeah, there's no figure we can share. Sorry. Yeah, and there's two things, right? Remember, the only thing I want to advocate today: do not do invasive modification to the IO frameworks. Yeah, you just clone the idea is that you clone the latest SGLang and everything works. And this multi-agent training is also how I want to demonstrate this idea. So everyone knows how a single agent training is being produced, right? So you have one environment, and you have a model running with inference engine, and your environment and your inference engine just some iteratively interact with each other for several times, and then it ends, and then you come back to the training. So if we just yeah, so in this time, if we can use that if we think that the environment is another agent, can we actually make it? So of course we can. The idea is that we launch two miles process, and one acts as agent A and another acts as the agent B. The agent B collaborates or interact with agent A. Then the agents A and agents B are trained at the same times. So that's the idea of multi-agent training at the same times. And there's some concrete example. So this one is sorry. I think this one is a doctor-patient co-training project. So it comes from the aunt groups. They're caring about the Medicares. So why we are training doctor and patients at the same time? Like we want the doctor to give more adequate solutions to the patients, and we want the patient to describe their problems in a more detailed way than the doctor can actually digest it. Right. So we train the doctor as the agent A, and we train the patient as the agent B, and then they are evolving together. Then we prove that the doctor can be better than just training the doctor itself, and the patients can also learn how to describe them in a more formal way. Yeah, and that's the first idea of doctor-patient co-training, multi-agent training with mice. And another thing we do is like a deep research agent. Um, Ideally speaking, that deep research agent does not need to be a multi-agent systems, but since if you are using agent to search against Google, yeah, so Google returns you a bunch of long context. So if you're just using one LLM to process with deep research, it may easy to exceed your context length. So we try to detach this job into a multi-agent systems. We have one planning agent that's try to decouple your problems into several steps, and we have a several steps agents that each agent take several steps and try to do them themselves, and then summarize it and return to the planning agents. So with these kinds of multi-agents, with our support of multi-agent training, so we can enable deep research we can enable this kind of deep research called training. We train the summarize agents to give better summarization, and we train the sub agents to search Google more smartly and gives more accurate summary. And we train the planning agents to give more adequate and to be more patient to give better like description. So everything works well with these kind of multi-agent training systems. I want to disclaim that the actual training is if you do not setting your learning rates and setting some training strategies carefully, the multi-agent training is really easy to collapse. But we have some successful stories, and we actually have published. You can go to this line to see the actual projects, and there's some experiments they have proven. Also, there are some experiment results they have given. Yeah, so that's the idea of multi-agent training, right? So have you have you ever think about how you are modifying SGLang or how you are modifying Megatron? You never, because when you are deploying agents, you do not need to care about this thing. So the idea is that if you are training the agents, you also do not need to care about this thing, and that's why I'm advocating. You just think Megatron and SGLang as a black box and utilizing these tools to enable your RL training, and what you expect is what you can get. Okay. Yeah, these figures showing that core training makes it better. Okay. This is should be more like technical. Okay, it's a unified FP8 training. Um. Uh, so, uh, was thinking about like we want to enable low precision rolling outs or low precision training in RL for long times. I guess yeah. I I also see Daniel there works on this. Yeah, yeah, admirable. Thanks so much. And for us, what we do is that ideally speaking, as I said it, ideally speaking, you don't need to launch SGLang with FP8. You need to do nothing. Yeah, that actually happens. For this work, we just change the checkpoint of SGLang. Sorry, we changed the checkpoint from BF16 to FP8, then launch it with SGLang. Then on SGLang side, everything works well. So the thing that we submit 0 lines of code change to SGLang, but we submit 3 commits to Megatron's transformer engine to help them solve some bugs. Then after the bug has been merged, we can enable a fully end-to-end FP8 training. The idea is that if you are training your model with BF16 compared with FP8, maybe BF16 training is slower but gives you better precision. But if you are trying to project or somehow like project your BF16 checkpoints from the training back to the FP8 rollout, you have to do calibration. Like this is a common problems when you are doing these kinds of low precision. Like you are project a BF16 checkpoint back to FP8, then you have to do calibration. If you do not calibrate it carefully, your rollout shall give you a bunch of garbage. But if you do not do calibration, if you're doing so careful calibration, it takes a bunch of times, and it's actually making FP8 train rollouts meaningless, since FP8 training should be like quicker. Yeah, but if you're doing carefully calibration, it takes a long time. So yeah, that actually hurts. So that's the idea of end-to-end FP8 training. We trained with FP8 and we inference it with FP8. Then directly transfer the trained FP8 checkpoint back to the inference. Everything works smoothly. Yeah. So there are several lines that demonstrating how this work is being finalized, and we have blog posts on our website on lmc.blog that you can see how we are doing this kind of unified FP8 training. Yeah, coming back is that we also have some heated topics like the BF16 QAT training, quantized aware training, and also like the interval weight only rollouts. You can maybe you can use your ADEN 100 GPUs to do RL with much faster time enabling these kinds of features. Okay, but I won't go deep into it today. Right. Okay, and another project I want to introduce of our team is that we enable the DeepSeek v.3 training. Sorry, I have speaking thousands of times, but since we do not do invasive optimization or change to SGLang, after DeepSeek v3.2 is released, we just update SGLang's version with the correct version of that supports DeepSeek v3.2. Then it should be work on miles. Yeah. But we still spend some time to debug and to modify the codes of Megatron. Yeah. So the good news is that we can now train DeepSeek with 3.2 with a with correct devices and with several lines of change of Megatron and with no change of SGLang. And we prove that we're using miles, you can do SFT for DeepSeek with 3.2 with correct loose gain. Yeah, this is a loose line, so it should goes down. Yeah, and also you can using mouse to do RL for DeepSeek with 3.2. This is the rewards. Yeah, it goes up and then it's stable. Okay. Yeah, this work is something like we call it routing replay. The idea behind this work is like miles we care about the large scale MOE model training, and for MOE model there's a routing system that when every token go into your one layer, then there's a router that try to send the token to the correct experts they may go to. So it is like for the dense model, each token going to the layer, it goes to everywhere. Then you get the outputs of that layer. But for MOE models, you only get to several parts of that layer, and then several parts of that layer, and then it gets the outputs. So in each forwarding, MOE models routers select which experts the token actually go to. And there's two kinds of forwarding in RL. First is the training forwarding. And the first is inference forwarding, and the second is the training forwarding. So the idea behind this is like the we want to replay the routing information in inference for training. That means the token in inference time, which experts generates these tokens should be the experts that's been trained. If one token is generated by expert A and expert C, you do not want next time you are training expert B and expert D because they are not responsible for them, right? Okay, so that's the idea behind this. We try to record the routing information when we are doing inference on SGLang side, and we replay this routing information when we are doing forwarding on Megatron side. Yeah, and that's the idea of routing replay, is make sure that you are training the right experts when you are doing RL. Yeah, so yeah, that's the idea. And this figure shows it clearly. It's coming from the Xiaomi's Mimo team. They recently open source their their best model up to date, and their model is actually being trained with SGLang's raw backend. Okay.
If I recall, Qwen and DeepSeek also have the same idea in their paper.
The R3?
The MOE replay.
Oh, okay. Good question. So it's slightly different. So there's a methodology called the R2, and I'm introducing R3. Yeah, so R2 is like recording another type of routing information and replay it later, but it is connected with like the like the off policy training for the policy model. So I won't go deep into it. But the idea of R3 is like more clear. You want to, yeah, those experts who generate the token should be those experts being trained. If token is being generated by expert A and B, you do not want to train expert C and D. Yeah, that's the idea. Okay, another thing, possibly this is maybe the final thing, yeah, like a unified multi-turn RL. Yeah, thanks. I think Charlie today, I mean the previous speaker, he introduced you guys what is multi-turn RL, right? So, take it back. If you think about multi-turn RL, it is like you are interacting with the agents. So when you're interacting with the agents, do you care about Megatron or do you care about whether it's served with SGLang? I think you never care about it. You just care about how you're interacting with it, or you care about how to define the behavior of your agents, right? So if you can clearly define your agents, I think it can be open. It can be open to train. So that's the idea of what is unified multi-turn RL. You just need to care about how to define your interaction behavior. Then you define the behavior with our customizable function. So all other parts should be working as we expected. It give you correct like masking, like padding, yeah. But everything you don't need to care about this thing. You just define how you interact with it. how you interact with your agents and then train it. Yeah. So that's the idea I want to suggest today with Miles. If you want to if you want to train an agent, you just need to define how you interacted with your customized rollout function. Then just write that function, pass it to Miles as a parameter. Then everything should work as you expected. Yeah. So the good news is that take this idea, we have successfully running the multi-turn agentic training with Megatron with Queen's small language model. Yeah, so we just change one function called the raw function, and the raw function maybe takes like 200 of lines of codes, and then you pass that code pass to as a parameter, and then the rewards goes up as you expected. Okay. Yeah, okay, thanks. No other things. Yeah, that's maybe all the topics I want to discuss. It's chiefly the latest updates of what we do with SGLang's RL community and what we do with Miles. Yeah.